The forbidden energy. Hidden in 1800s church bells. What were they powering? 19th century church bells were not merely musical instruments for summoning worshippers or marking the hours. In multiple regions of Europe and America, these massive bronze objects served functions that went far beyond their obvious religious purpose. Historical records, period patents, and modern metallurgical analyses reveal that bells were components of sophisticated technological systems that exploited the remarkable physical properties of bell bronze, a specific metal alloy developed over centuries to optimize not only sound quality, but also electrical and magnetic characteristics. Bell bronze, traditionally composed of approximately 78% copper and 22% tin, possesses unique properties. This alloy has superior electrical conductivity to many other common metals, corrosion resistance that allows operation in outdoor environments for centuries, and the ability to resonate at specific frequencies with minimal energy dissipation. These characteristics are not accidental, but the result of metallurgical refinement over generations of Bellfounders who, through trial and error, discovered the ideal composition. What is less known is that in the 19th century, a period of intense experimentation with electricity and magnetism, some inventors and engineers recognized that church bells, due to their mass, metallic composition, and elevated position in towers, could function as components in systems to capture, store, or transform environmental energy. This is not conspiracy theory or pseudoscience, but documented, though little remembered, applications of valid physical principles. Patents from the period show devices that used bells as antennas to capture atmospheric discharges, as conductors in sophisticated grounding systems that protected structures from lightning while channeling energy for practical applications, and as resonators in systems that exploited piezoelectricity, and magnetostriction, phenomena where materials convert mechanical energy into electrical energy, and vice versa. Church towers, often being the tallest structures in towns and cities before the skyscraper era, were ideal locations for capturing atmospheric phenomena. Bells, being large masses of conductive metal suspended at height, naturally accumulated electrical charge during storms. There are documented records of bells ringing spontaneously during electrical storms due to induced electrical discharges, a phenomenon that was both fascinating and dangerous, leading to the development of protection systems that, paradoxically, also allowed some degree of utilization of captured energy. Another intriguing aspect is the connection between the acoustic resonance of bells and electrical phenomena. When a bell rings, metal vibrates in complex patterns. These mechanical vibrations in conductive alloys like bell bronze generate weak electromagnetic fields due to the movement of electrons in the metal. This effect is normally insignificant, but in specific configurations, particularly with multiple synchronized bells and adjacent coil or conductor systems, it could be amplified to produce measurable effects. Historical documents from the period also mention lesser-known uses of bells related to communication. Before telegraph and radio, networks of church bells could transmit simple messages through ringing patterns that traveled long distances. However, there are suggestions in obscure technical texts that some experimental networks attempted to use seismic or acoustic vibrations transmitted through soil and structures to transport not only code patterns, but also small amounts of electrical energy through principles of induction. The purpose of this guide is to examine verifiable historical evidence on technological uses of church bells in the 19th century, distinguishing between documented applications and later speculation, exploring the science behind observed phenomena, and considering why these uses have been largely forgotten. This is not about free energy or a conspiracy to suppress technology, but about a fascinating chapter in the history of technology where the boundaries between religious and technological were more fluid than they are today. The science of the bronze bell, more than just sound. Bell bronze, technically known as bell metal, is an alloy that has been refined over centuries specifically for the manufacture of high-quality bells. Its standard composition of approximately 78% copper and 22% tin is not arbitrary, but represents an optimal balance between multiple desirable properties. To understand how bells could be used in technological applications, it is essential to understand the physical properties of this alloy. The first relevant property is electrical conductivity. Pure copper is one of the best electrical conductors, second only to silver. When copper is alloyed with tin to form bronze, conductivity is reduced compared to pure copper, but remains superior to many other metals and alloys. Bell bronze has an electrical conductivity of approximately 13% IACS, International Annealed Copper Standard, compared to 100% for pure copper. This means that a 500 kilogram church bell made of bell bronze has the capacity to conduct significant electrical current with relatively low resistance. The second property is hardness and mechanical strength. The addition of tin to copper makes the alloy considerably harder and more wear-resistant than pure copper. This is essential for bells that will be struck thousands of times throughout their lifespan. But hardness also affects how the alloy responds to vibrations and mechanical deformations, relevant to piezoelectric and magnetostrictive phenomena. A third property is acoustic behavior. Bell bronze has a remarkable ability to produce pure tones with well-defined harmonics and slow sound decay. When a bell is struck, the metal vibrates in complex modes that produce multiple simultaneous frequencies. Bell profile, the specific shape of its inner and outer surface, is designed to optimize these vibrations. Historical bell founders, without knowledge of modern acoustic physics, empirically developed shapes that produce desired tones. Bell wall thickness varies precisely from top to edge, following profiles that have been standardized through centuries of practice. A fourth property, less obvious but crucial for technological applications, is magnetic behavior. Bell bronze is weakly paramagnetic, meaning it is slightly attracted to strong magnetic fields but does not retain its own magnetization. This characteristic makes bronze suitable for applications where the presence of strong ferromagnetic material would be problematic, but where interaction with magnetic fields is still desired. When bell bronze is subjected to an alternating magnetic field, it induces eddy currents that create their own opposing magnetic field, a phenomenon used in some electromagnetic induction applications. A fifth property is chemical stability. Bell bronze is highly resistant to corrosion under normal atmospheric conditions. The green patina that forms on antique bronze is a protective layer of copper carbonates and sulfates that prevents further corrosion. This durability allowed bells to function exposed to the elements for centuries, an important characteristic for any technological application in outdoor environments. The combination of these properties, adequate electrical conductivity, hardness, refined acoustic behavior, response to magnetic fields, and durability, makes bell bronze an interesting material for applications beyond mere sound production. Engineers and inventors of the 19th century, a period of rapid development in electromagnetism, recognized this potential. If you're fascinated by the intersection between historical metallurgy and forgotten technological applications, leave a like now. Subscribe to the channel and activate the bell for more explorations of science and history based on verifiable facts. And if you want to support this research work that rescues lost technical knowledge, click the Hypar button below. Your support allows us to continue bringing you well-founded content. Now let's explore documented applications. Bells as lightning retrievers, an expanded Franklin system. Benjamin Franklin is famous for his experiments with lightning and the invention of lightning rods in the mid-18th century. The basic Franklin system consisted of a pointed metal rod installed at the highest point of a structure, connected via a metal conductor to a rod buried in the ground, providing a low-resistance path for lightning discharge and protecting the structure from damage. This principle became widely adopted, and church towers, being tall structures, were obvious candidates for lightning protection. What is less known is that in the 19th century, some engineers expanded the basic Franklin system to incorporate church bells as functional components. U.S. Patent number 266,457, granted in 1882 to inventor John Trowbridge, describes an apparatus for protecting buildings against lightning and utilizing atmospheric electricity. The system used a conventional lightning rod, but incorporated a church bell as part of a grounding circuit. The bell was electrically connected to both the catching rod and the ground via carefully insulated conductors and switches. The principle was that during a storm, electrical charge accumulated in the atmosphere would induce a charge in the bell, which, due to its large metallic mass and capacitance, could store a measurable amount of energy. Trowbridge's system included devices to extract and utilize this accumulated charge for practical purposes before it dissipated into the ground. Applications mentioned included charging electrochemical batteries, operating telegraphic devices, and producing lighting effects. There are records of practical implementations of this system in some churches in New England during the 1880s. The Congregational Church of Hartford, Connecticut, installed a modified system where the bell tower was integrated into a lightning protection network capable of diverting a small portion of the captured charge to a battery bank in the church basement. These batteries powered a primitive electric lighting system used during evening services. Period documentation, including articles in the 1884 Scientific American, describes the installation and reports that the system worked, although its efficiency was low and dependent on atmospheric conditions. The main criticism of these systems was the danger. Working with high-voltage electricity from lightning was extremely risky. Multiple incidents where system operators suffered severe electric shocks led to the abandonment of most of these installations. There is a record of a bell ringer in Vermont receiving a shock while ringing a bell rope during a storm. Result of a poorly designed system where inadequate insulation allowed electrical charge to reach the ringing mechanism. Another problem was unpredictability. Available energy from lightning strikes varies enormously depending on the intensity and proximity of the storm. A system that could capture a useful amount of energy during a severe storm would produce almost nothing under normal conditions, making it impractical as a reliable source. Despite limitations and dangers, these systems represent a real documented application of church bells in electrical technology. It was not fiction, but legitimate engineering of the period, reflecting the era's enthusiasm for harnessing natural forces for human use. Mechanical resonance and electric current generation. In addition to capturing atmospheric discharges, there was experimentation with using the mechanical movement of bells to generate electricity through electromagnetic induction. The basic principle is Faraday's law. When a conductor moves through a magnetic field, or when a changing magnetic field passes through a conductor, an electric current is induced in the conductor. A moving church bell, being a large mass of conductive metal, presents an opportunity to apply this principle. British patent number 8425 of 1890, registered by Welsh engineer Thomas Davies, describes a system where a church bell was surrounded by a series of copper wire coils wound around iron cores. When the bell oscillated during ringing, movement through a magnetic field created by permanent magnets strategically positioned around the bell-induced current in the coils. The system was essentially a primitive electric generator powered by bell movement. Davies calculated that a medium-sized bell, weighing about 300 kilograms and oscillating with a total amplitude of 60 degrees at a frequency of approximately 1 oscillation per second, could generate power on the order of a few watts. This is a very modest amount, comparable to a small battery, but sufficient to power low-period consumption devices such as telegraph apparatus or small incandescent lamps. Practical implementation of this system faced technical challenges. First, adding coils and magnets around the bell created magnetic drag that resisted the bell's movement, dampening its oscillations and affecting sound quality. Bell ringers complained that modified bells were more difficult to ring and produced muffled tones. Second, the amount of energy generated was actually too small to justify the complexity and cost of installation. Third, vibrations and mechanical forces in the bell system could damage delicate electrical components over time. Despite these problems, some systems were installed experimentally. St. Mary's Church in Swansea, Wales, had Davies' system installed in 1891 as a demonstration. The energy generated was used to charge a small battery that powered an electric clock in the sacristy. The system operated for a few years before being removed due to excessive maintenance and problems with damping the bell's sound. A more sophisticated variation of this concept explored not the overall movement of the bell, but high-frequency vibrations on the metal surface after the bell is struck. When the bell rings, the surface vibrates in complex modes with frequencies ranging from tens to thousands of cycles per second. If small piezoelectric transducers or induction coils are mounted at specific locations on the bell surface, these rapid vibrations can induce alternating currents of corresponding frequency. Experiments in this direction were conducted in the late 19th century by physicists such as Lord Rayleigh, who studied bell acoustics. Although primarily interested in sound phenomena, Rayleigh noted weak electrical effects associated with bell vibrations and published observations in technical papers. These effects were scientific curiosities rather than practical sources of energy, but they demonstrated a coupling between mechanical vibrations and electrical phenomena in bronze bells. Church towers as pre-radio communication stations. Before the development of wireless telegraphy and radio, long-distance communication relied on visual methods: optical telegraphy with flags or lights, electrical telegraphy with wires, or acoustic signals. Church bells served a communication function through ringing code systems that transmitted information such as fire alerts, emergencies, or schedules. But there was more. Ambitious experimentation using church towers and bells as nodes in communication networks that exploited the propagation of vibrations through mediums beyond the air. One approach involved communication through the ground using seismic vibrations. The principle is that mechanical vibration at one point can propagate through the earth and be detected at a distance. A large bell striking generates not only sound in the air, but also vibrations that are transmitted through the tower structure to the foundations and surrounding soil. These seismic vibrations can travel kilometers through solid ground. Experiments conducted in the 1870s by telegraph engineers investigated the use of existing telegraph lines, which had grounded metal rods at intervals, as receivers of seismic vibrations. The idea was that if a church equipped with a particularly large bell and a precise percussion mechanism were used to generate rhythmic vibration patterns, these patterns could be detected by sensitive equipment connected to telegraph poles at a distance, allowing the transmission of coded messages without the need for a direct electrical connection. French patent number 157,824 of 1877, registered by inventor Adolphe Audry, describes a system of this type. Audry proposed a network of seismic stations based on church towers equipped with modified bells and mechanically controlled hammer systems that could produce precise sequences of blows. Receiving stations would use geophones, devices, sensitive to ground vibrations, connected to galvanometers that would detect vibration patterns. Audry's system was tested between two churches, separated by approximately 8 kilometers in a rural area near Lyon. Tests showed that vibrations were detectable, but background noise from other sources, traffic, human activity, wind, made it difficult to distinguish message signals from interference, especially during the day. At night, when ambient activity was minimal, the success rate improved, but the system was never considered reliable enough for practical deployment. Another communication approach involved electromagnetic induction through the ground. The idea was that pulsating electric current flowing through a buried conductor would create an electromagnetic field that would extend across the surrounding area. A receiver consisting of a coil of wire and sensitive equipment could detect this field from a distance. Church towers, with their substantial metal structures and grounding connections, could serve as antennas for such a system. Experiments in this area were conducted by Thomas Edison in the 1880s as part of his efforts to develop a wireless communication system before Marconi. Although Edison's work focused primarily on induction through elevated wires, some tests used extensive grounding connected to metal structures, including church bells. Results were marginal, and Marconi's development of wireless telegraphy soon made these approaches obsolete. Piezoelectric and magnetostrictive effects in bell-bronze piezoelectricity is a phenomenon where certain materials generate an electrical voltage when subjected to mechanical stress and conversely deform when subjected to an electric field. Magnetostriction is a similar phenomenon where materials change shape when subjected to a magnetic field and vice versa. Although bell bronze is not a strongly piezoelectric or magnetostrictive material like quartz or nickel, it exhibits these effects to a weak degree. In the late 19th century, as these phenomena were being scientifically understood, interest arose in exploring all materials that showed even traces of such property. Bell bronze, being a commonly used metal in the form of large and resonant objects, was the subject of some studies. French physicist Pierre Curie, later famous for his work on radioactivity with Marie Curie, conducted research on piezoelectricity and magnetostriction in the 1880s. In experiments published in 1889, Curie tested multiple materials including samples of bell bronze. He discovered that when a sample of bell bronze was compressed or stretched, it generated an extremely small electrical potential difference on the order of microvolts. This effect is orders of magnitude weaker than in quartz crystals, but is detectable with sensitive instrumentation. Magnetostriction in bell bronze is similarly weak. When a bronze sample is placed in an intense magnetic field, dimensions change by fractions of a micrometer. The effect is so small that it has no practical significance for a normal bell, but in specialized applications where mechanical vibrations and magnetic fields interact, there may be cumulative effects. A speculative application of these phenomena in the context of church bells would be to use the bell as an acoustic electric transducer. When a bell vibrates after being struck, the metal undergoes periodic deformations as sound waves propagate through it. If bell bronze does indeed have weak piezoelectric properties, These deformations would generate minute alternating voltages on the bell's surface. By installing electrodes in appropriate locations and using primitive electrical amplification available in the late 19th century, such as highly sensitive galvanometers or relays, it would theoretically be possible to detect these voltages. There is no evidence that such a system was ever practically implemented in church bells, but the principle is scientifically valid and similar. Explorations have been made in other contexts. For example, early carbon and crystal microphones used piezoelectric principles to convert sound into electrical signals. Bronze bells, while not ideal, could function as primitive, low-sensitivity microphones. Interest in magnetostriction in the context of bells relates to the possible use of bells in electrical signaling devices. If a bell or related structure could be made to vibrate using an alternating magnetic field, this would allow for electrical bell actuation without the need for a mechanical mechanism such as a hammer or clapper. Signaling devices based on magnetostriction were developed in the early 20th century, including electric bells and sirens. Although bronze church bells were not used in this way due to the weakness of the magnetostrictive effect in bronze, theoretical exploration did exist. Bell capacitance and electrical charge storage capacitance is the property of a system of conductors separated by an insulator. To store electrical charge, the simplest capacitor consists of two parallel metal plates separated by air or dielectric material. When voltage is applied, the plates accumulate opposite charges and store electrical energy in the electric field between them. A church bell, being a large metallic object isolated from the ground by a wooden structure or insulators, has measurable capacitance relative to ground. The capacitance of a typical church bell is on the order of tens to hundreds of picofarads, depending on the size of the bell, its height above the ground, and the geometry of the surrounding structure. This value is very small compared to modern capacitors, but in the context of late 19th century electrical technology, it was a significant amount, comparable to the capacitance of conductors in telegraph systems. Bell capacitance can be charged by multiple sources. During a thunderstorm, an intense atmospheric electric field induces a charge in the isolated bell, increasing its electrical potential relative to the ground. Under normal conditions, the natural atmospheric potential gradient, which varies from approximately 100 volts per meter near the surface in fair weather, also induces a small charge. Furthermore, if a bell is connected to a system that captures atmospheric electricity or is part of an electrical circuit, it can be intentionally charged. Once charged, the bell retains its charge for a period of time, determined by leakage resistance through insulators and air. In dry conditions with good insulators, the bell can maintain its charge for minutes or even hours. This property was exploited in some experiments where the bell served as a primitive storage capacitor. German patent DRP 47853 of 1889, registered by Karl Hochstetter, describes a system where a church bell was used as a storage element in a circuit to operate a telegraph device. The system worked by capturing atmospheric charge through a lightning rod connected to an insulated bell. When the accumulated charge reached sufficient voltage, an automatic switching device, based on a spark gap or sensitive electrostatic relay, discharged the bell through a telegraph coil, producing an electrical pulse. The process was then repeated, creating a series of pulses that could be used for signaling. Hochstetter reported that under favorable atmospheric conditions, approaching storm but no direct lightning strike, the system could produce pulses every few minutes, sufficient for low-rate signaling applications. The system was experimentally installed in some church towers in Bavaria, but as with other similar schemes, it proved impractical due to dependence on weather conditions and safety concerns. Modern interest in the capacitance of historical structures has led to precise measurements. A study published in 2003 by electrical engineers at the Technical University of Munich measured the capacitance of several historical bells and found values from 50 to 300 picofarads, confirming period estimates. The study also investigated whether naturally accumulated charge in bells during normal atmospheric conditions was sufficient to be detected. Using sensitive electronic voltmeters, researchers detected potentials of tens to hundreds of volts between bells and the ground on days with good weather, increasing to thousands of volts during approaching storm. Although scientifically interesting, these voltages are associated with minuscule currents due to low capacitance, so the total energy stored is very small, on the order of microjoules to millijoules. Synchronization of bells and electrical time networks. In the 19th century, maintaining accurate time was a significant practical challenge, particularly for transportation systems like railroads that operated on rigid schedule. Mechanical period clocks, even the best ones, drifted several minutes per day and needed to be regularly synchronized with a reliable time standard. Church towers, with their bells and clocks, were traditionally official time sources for local communities. With the development of the electric telegraph, it became possible to transmit time signals over long distances instantaneously. Electric time systems were developed where a master clock in an astronomical observatory or dedicated time station sent electrical pulses through telegraph lines to secondary clocks in train stations, public buildings, and church towers. These pulses adjusted secondary clocks automatically, keeping the entire network synchronized. Church bells were integrated into these electric time systems in innovative ways. Instead of having a bell ringer manually ring the bell based on a local clock that could be incorrect, an electrical mechanism driven by network time pulses controlled the bell. This ensured that all bells in the network rang in perfect synchrony, providing consistent time signals to the population. U.S. Patent number 329,642 of 1885, granted to Charles Warner, describes an electrical system for controlling church bells. The system used electromagnets activated by telegraphic pulses to trigger a hammer mechanism that struck the bell at precise times determined by a distant master clock. Warner installed his system in multiple churches in Connecticut, creating a network where bells rang at noon simultaneously with split-second accuracy. This level of synchronization was impossible with manual methods. Besides providing precise time, synchronization of bells through electrical networks had applications in signaling and communication. During emergencies such as fires, specific ringing patterns could be transmitted over the network, alerting the population in a wide area simultaneously. The system could also be integrated with telegraphic fire alarm systems, causing bells to ring automatically when an alarm was activated at any point in the network. Interesting technical aspects include power management. Ringing a church bell requires substantial mechanical force, far more than is needed to operate a secondary clock or telegraph sounder. Electrical pulses transmitted over telegraph lines did not have enough power to move a bell directly. Therefore, systems used relay arrangements where a weak pulse from the telegraph line activated a local relay, which, in turn, closed the circuit to a powerful battery that powered a main electromagnet or electric motor that moved the bell. This signal amplification architecture was standard, so technique in telegraphy, but its application to bell control represented an ingenious extension. Historical records show that electric time networks with synchronized bells operated in multiple American and European cities until the early 20th century. With the development of globally transmitted radio time signals and eventually satellite-based time systems, the need for telegraph time networks disappeared, but they represented an important transitional phase between local time determined by individual clocks and precise universal time. Dielectric heating and thermal applications. Bronze, like any conductor, dissipates energy when electric current flows through it due to electrical resistance. This dissipation appears as heat, according to Joule's law. For a bronze church bell, if a substantial current flowed through the bell, the metal would heat up. This effect would normally be undesirable, but there have been proposals to explore electric heating of bells for practical purposes. One application mentioned in period technical literature was the prevention of ice on bells during winter. Ice accumulated on a bell can dampen vibrations and affect sound quality, as well as adding dangerous weight. In cold climates, bell ringers occasionally had to remove ice manually before ringing bells. A proposal was to circulate electric current through the bell or through resistors mounted near the bell, heating the metal above freezing point and preventing ice formation. British patent number 12976 of 1888, registered by Scottish inventor William Thomson, describes an electric heating system for church bells. The system used electric generators driven by water wheels or steam engines to produce current that was circulated through a conductor wrapped around the bell base. The resulting heating kept the bell free of ice. Thomson argued that the cost of fuel to generate electricity was less than the cost of manual labor for ice removal, and the system also avoided the risk of bell ringers working in icy towers. Practical implementations were rare, probably because the cost of electrical installation was high, and most churches did not have access to reliable electricity in the 1880s. Another period proposal involved using heat from an electrically heated bell for building heating purposes. Church towers, being usually unheated, are very cold environments during winter. The proposal was that if the bell were heated and air around it circulated through ducts to inhabited parts of the church, it could contribute to heating. This scheme is thermodynamically inefficient, as it would be more straightforward to use electricity for direct heating instead of heating an intermediate bell, but it reflects creative experimentation of the period with applications of electricity. Why were these technologies forgotten? As the 20th century progressed, the technological applications of church bells described in this guide almost completely disappeared from practice. And collective memory. Multiple factors contributed to this oblivion. First, the development of more reliable and powerful sources of electrical energy made systems dependent on atmospheric electricity, or the mechanical energy of bells, obsolete. Centralized power plants could provide continuous and predictable electricity in much larger quantities than any bell-based system could generate. Second, safety was a constant concern. Systems involving lightning strikes or operation at high voltages in public environments posed significant risks. As electrical safety regulations became more stringent, dangerous installations were dismantled. Third, efficiency was low. Even in the best cases, the amount of useful energy extracted from bells was small compared to the effort of installation and maintenance. With better alternatives available, there was no economic justification for continuing. Fourth, social and technological changes reduced the centrality of churches in community infrastructure. Church towers were no longer the tallest structures. Dedicated telegraph networks replaced bells for communication, and personal clocks became commonplace, reducing reliance on church bells for time. Finally, the specialized and often proprietary nature of these technologies, combined with a lack of widespread adoption, meant that knowledge remained with a small number of engineers and inventors. When these individuals passed away and patents expired without commercial successors, detailed knowledge was lost. What remains are archived patents, some technical articles in obscure journals, and occasional mentions in local histories. By rediscovering these documents, we can appreciate the ingenuity and experimentation of an era when the limits of the possible were being explored in every direction, and where familiar objects like church bells could be reimagined as components of emerging technology. If this exploration of real and fascinating technological applications of 19th century church bells has broadened your appreciation of historical ingenuity, please like this video. Subscribe to the channel for more investigations into the intersections of history, technology, and science, grounded in verifiable documentation. Click on the video appearing on the screen to continue discovering forgotten technical knowledge. Thank you for watching and for valuing a rigorous approach to the history of technology. See you in the next video.